Hey guys, your boy Chili here. Welcome back to C++Asio. I'm very excited today. We're going to be looking at coroutines. Everything in this series has been building to this. This is what I wanted to do, and everything has just been preparation for that. And I mean, it's been all good stuff in its own right. We've learned about, ACO, and we've learned about networking and HTTP, and that's all well and good. But what I really wanted to show you is coroutines. It's the thing that makes this nastiness go away, right? And the reason why we do this nastiness is because if we do things synchronously, we can only handle one connection at a time. If we could do it, we could do more connections if we spawn multiple threads, but that has a lot of downsides. It's not as performant, it uses more system resources, and it also requires you now to synchronize between threads, which, as we all know, is just that's a bug farm. If you can avoid it, you want to avoid it. Async allows you to avoid it, but the traditional way of doing async with callbacks is it's this, right? It's not great. So now we're going to bring it back with C++ coroutines, which is great because I wanted an excuse to show off and play around with C++ coroutines. They've been in here for a while, but you hardly see them because the support has been at a very low level. And so you have to use specialized libraries, or you have to do some crazy C++ in order to actually get at them. So before I start here, just notice that I've added some boilerplate code. I added the header and source file for our coroutine implementation of the fetch function. And, I've added the CLI option to enable that. And in main, that's switched in here. But let's get down to it. Let's get down to the meat. So to do it with coroutines, we have to create a coroutine. A coroutine is just, it's a function, but it's a special function. There are a couple things that make it special. One is that it has to return an awaitable type. So, I mean, we could create a function that returns an awaitable type, but let's do it all inside here like all our other implementations. Let's do it with a lambda, which we can do. We're going to call this our strand. We're going to spawn one strand per URL that we're trying to process. So let's take that in as a parameter. And now here's the special sauce. We have to say that this lambda is returning an awaitable type. That's what's going to key in that this is a coroutine. The compiler will compile this as a coroutine. And the awaitable type in ACO is named awaitable. And awaitable types, they can return a value when the coroutine has finished. So now we're no longer restricted in, like binding in a reference to something in a vector and then filling that slot in. We can return a value like a normal ass function, which is nice. So of course we're going to return our response type. And inside here we're going to do all our operations, and it's not going to look like it does in here. It's going to look more like this, with just a flat sequence of steps that we take. You might be wondering, do I absolutely have to do this? Like, can't I just return an awaitable and, like a normal lambda, it'll just deduce the return type? But no, for lambdas, you actually have to put it in here. It can't be deduced for awaitables. It's a special case. So because we're returning a response, we should probably create that response object that we're going to eventually return. We can initialize its URL in there. We now create our boost URL based on that URL string. That'll have all the different components parsed out for us. And here comes our first grand step. We need to do a resolve on our resolver. So normally we would call resolve an asynchronous function, but we're doing async resolve. So we call async resolve. And in here we're accustomed to passing in a callback that is going to take in the result of that, the endpoint that has been resolved. But with coroutines, we don't do that. We do it much sexier. We can actually just do auto np-iter is equal to async resolve. We can get the value just out like a normal function call. So as usual, we have to pass in the query, which is the same, and we pass in the resolve token. Now remember, I said that in ACO, it's kind of nasty. Like normally we would pass in a callback here, and it would be nice if we could see the signature of the callback. Like what kind of a function object is it right in here in the IntelliSense, but we can't see that. And the reason for that is because this resolve token isn't just a callback. It could be many different things. If you're doing with callbacks, you pass the callback in directly. But if you're doing it with coroutines, you pass it just a token value that tells this function you have to behave as a coroutine. You have to return an awaitable type. So we do as use awaitable. And that is the secret sauce, that's the token that tells this thing you're going to work in coroutine mode, in awaitable mode. So now this function is going to return, you can't see it because you can just see a whole bunch of, template metaprogramming bullshit in here. But what this is actually returning is an awaitable type like this. It's an awaitable wrapping an endpoint iterator. And so what you have to do now is await that awaitable to get out the value that it's wrapping. So this is where the new C++ stuff comes in, co-await. This is a keyword that's been in here for a while. You've likely never seen it or used it, but this is what you do when you're calling a function that is awaitable. You await that function, and now this strand is effectively going to go to sleep and only wake up when this resolve and this async resolve operation is done, and then you will get out the iterator and resume. And I'm going to talk a little bit more about how that works after we're finished here, but let's do a few more steps. This is the basic flow. We are going to call an async function with a use awaitable token, and we're going to await it to get out the value directly that we're interested in. And while you're here, I want you to notice one more thing. We're not getting any error code. We don't need one, because if there's an exception somewhere, the result of co-await is going to throw an exception, and that will propagate out to our catch in main. And so we actually don't have to manually handle every single error. It works just as cleanly as it did in our synchronous version. So unlike callbacks, we can just use exceptions the way that they're meant to be used. Now the next thing we're going to add in here is our socket. And we can just create this as a local variable, because unlike callbacks, this is now going to live to the end of our strand, to the end of our whole sequence. And so we don't have to worry about creating like a shared pointer and binding it into every callback and passing it along the chain. You just create it like a normal local variable and you're done. And now we call async connect. We pass it the same things we've been passing it before, except the token is going to be use awaitable and we have to co-await it. It doesn't give us any interesting information besides, well, I mean, it does give us the endpoint iterator. We could look at that, but we don't care. So we don't have to do anything with the return value. It's a similar story with the handshake. Again, we just await that, pass it the same things, except we pass it this token here. Here we're going to build up our request. We're going to call async write. Buffer here, everything's the same except for this and this. Those are the only two things that are different. Now we create our string stream for building up the content. Here is our resizable buffer. We're going to put the header in there, and we are going to co-await async read until. Same story, but now we get out a value that we actually are interested in. The number of bytes that were read. The number of bytes up until this delimiter. And then we do resize and overwrite. Again, that's all the same. And if there's anything left in the receive buffer after we have pulled out the header part, we're going to put that into the beginning of the content stream. That's why we have to create the content stream up here. And now we're going to do our loop of reading into the fixed buffer and then transferring that into the content stream, just to make things the same as we did in the other two implementations. Here things get a little more interesting. In the callback, it got very nasty. We had to like create this inline context to hold all the different stuff, to hold the function, and then we basically do this callback recursion where the callback calls itself until there's no data left. So the callback keeps scheduling another call to itself. And we don't have to do this BS. We can just do a loop like we had originally in the sync version. But the loop has to be a little different. So let's just copy this as like a starting point and then see where we go from there. So the first question is, okay, so we're not going to do read. We're going to do async read. Now async read is going to take in a socket. It's going to take in the buffer. The third thing it's going to take in is, you guessed it, it's your boy, the completion token, which in our case is going to be use awaitable. But what we want to do here is, instead of having this one throw an exception, in this specific case, we want to use error codes. Because if you remember, this thing throws an exception for things that aren't errors, which is not my favorite little design choice, but it is what it is. So for this one, we actually want to get an error code, check it, and only throw as an exception if it's not end of file. If the problem was end of file, which is not a problem, we just want to finish. So how do we pass it the completion token while also passing it a reference to the exception code that it has to fill? it's tricky. This is something that you're probably going to have a hard time finding yourself unless you really dig into the documentation or you follow a tutorial. There's a function called asTuple, and it allows you to basically modify a completion token and get the function to behave a little differently. So we are going to modify use awaitable because that's the type of completion that we want. But when we add asTuple in here, what that's going to do is instead of now throwing an exception, it is going to return a tuple containing both the original return value and the error code packed together in the tuple. And so now what we can do is we could use the tuple directly with get, but nicer way to handle that is just to destructure that tuple into its two components right here in line. So we're going to say, okay, I want you to destructure this into error code and number of bytes. Now, I know what I'm missing here. I'm missing the co-await. Yeah, because I copied that from the other place. All right, so that's fine. Put the const back here. I'm not sure if you need it or not. Okay, but anyways, so we've got our error code now. We've got our number of bytes, and we're going to check the error code. Throw an exception if it's a genuine error. If not, we're going to resize. We're going to output the fixed buffer into the content stream. And here's the problem: we can't actually use this variable that's created in here in our while. So what we're going to do is we're just going to go while true, and then down here, if there is an error code, let's break out of this loop. And we can do that because we've already checked for errors other than end of file. So the only other error it could be is end of file, and if it's end of file, we want to stop looping. And there you go. There is our reading loop all done up with coroutines. And I think you'll all agree it is somewhat better than this thing here. Just a little bit. There's a little secret sauce that you got to remember here is asTuple will allow you to get out that error code so that you don't have to deal with non-error exception. And after this is done, our content stream should contain all the content. So now we just go response.content is equal to content stream.string. We fill that bad boy out. And now we want to return the response. And you should use other keyword here added with coroutines, co-return. So now we return that response. And you can see in here, at every point where we had a callback in our callback implementation, now we have a co-await. Every time there is an asynchronous operation that we have to wait on, there's this co-await keyword in here. And at the very end, we have co-return to return the result. So here is our strand. Here's our coroutine, but we've just created it. How do we actually execute it on our IO context? Well, what you do here is you go Asio co-spawn. This is going to spawn a coroutine into the IO context. Start it running. So you pass it your IO context. You pass it your coroutine. You could pass it the naked coroutine if it doesn't take any parameters, but if it takes in parameters, you can call the coroutine. It will return an awaitable, and that awaitable will be spawned on the IO context. So it can take the naked coroutine function itself, or it can take in the awaitable that you get out when you call the function. And so what we want to do is we want to spawn one coroutine for each URL that we're processing. So we actually want to do a loop here. So we're going to loop over every URL, and for each one of those bad boys, we're going to call spawn. I'm going to pass in the URL into our strand. And so what you often do with co-spawn is you would pass it detached, meaning just run this coroutine freely, and whenever it's done, it's done. We don't care. Just like detaching a thread. But in our case, we actually want to, because this is returning a response, we actually want to maintain some attachment to this coroutine and to be able to get the response when it's done. So we can go use future. This is another completion token that you can actually use with asynchronous operations as well. But this will now return a future, which is, it's a std future. And if you've been following my series, you already know a lot about how std future works. So we're going to get a future for each one of these strands that we can then use to finally get the result. So we can create a vector of these response futures, and then we can do response futures dot pushback We can push back into those all the futures that we get from spawning these strands. So now these strands are going to be running on the IO context when? Only after we call IO context.run. And this is going to run until all those strands have finished. So when we get to here, we expect all these futures to be available and we can just get their responses immediately. So we could like loop over all of these responses. We could create a vector of responses, loop over all the futures, and for each one call get and push back into our vector of responses. But I'll show you a little sexy sauce here. Return response futures, and we're going to transform those by calling std future response get. So we're going to call get on every one of those futures in this range to get us a range of response objects, and then we're going to transform that range of response objects into a vector of response objects, and we should just be able to return that immediately. Oh yeah, I always forget that this one, it's actually a function, not an object. There we go. And that is beautiful, right? Nice little one-liner for you instead of, 4 or 5 lines of code. And I mean, if you wanted to be consistent, you could replace that loop with one of these bad boys where we're just transforming URLs by co-spawning. So we're transforming URLs into futures, putting them in the vector of futures, and then we transform that vector of futures into a vector of responses. Little ranges for you there. Of course, you can do this with loops. If you're not comfortable with ranges, that's fine as well. It's all good. So here we get a build success. Now, moment of truth. Let's run it with the mode async coro. And it's working fine. Beautiful, beautiful baby boy. All right, let's build this in release and do some numbers. So we start with no mode option. It's going to default to sync. Then we get 2.3 seconds. With async callbacks, we get 1.12. And with async coro, we get 1.07, which we would expect these to be mostly equivalent. I have found for some reason that the coroutine one is actually somehow it's a little faster. It doesn't make sense to me. It could just be randomness. But in any case, we get the same performance as our callback version. But I mean, you be the judge. Would you rather do this, or would you rather do this? With all this beautiful little tail here, all these error code checking cases. I think you can guess which one that I'm going with. And again, like the benefits in terms of the clarity of your code, I mean, it goes without saying. You don't have all this, indentation and nesting that you get with the callbacks, which again, like I said before, you can fix the indentation problem by making these all separate functions, but then you got like a whole bunch of different functions chilling out, and it makes things a lot more complicated. Here, it's just one straight line going down. It can't get any simpler than this. And the other huge, downside of callbacks, which you really can't get away with even putting them in separate functions, is that now you got to check every single goddamn error code, and it looks like this. And the beauty with coroutines here is it basically captures and marshals your exceptions. And that is also enabled here by the fact that if we were to spawn these detached, exceptions would terminate the coroutine, but they would just go into the void, right? But because we have a future, whenever we get an exception, it terminates the coroutine. The future is completed with the error, and then when we get around to calling get is when that exception will spring out again, and we'll be able to capture it and do something with it. Read it, get information out of it, learn about what went wrong. So the two reasons why we do future here is 1, because we want to get this return value, and 2, because we want to get any exceptions that were thrown. Now the topic of how coroutines work is a very deep topic, and it is not going to be covered in this video, of course, but to give you a general idea of what's going on here, you think of a coroutine, it's a function, but it's a function that can be paused and resumed. That's the thing. That's the special sauce. So whenever you see a co-await here, that is a point in the routine, a point in the function where it can pause, exit, and at some future time can come back and start from here. It doesn't have to start like a normal function. Always has to start from the top. That's the entry. Coroutine can start from the middle. If it was paused here, when you resume it, it is going to start from here. And so when you await some other awaitable, like the awaitable that comes out of here, function is going to pause. Your IO context is going to queue up a resume that is tied to an event, the event of this thing that you were awaiting. So we're going to pause our strand and we're going to set it up so that it only gets resumed after the resolve operation has completed and the event is signaled. We're going to get that event signal and we're going to look and say, we got to resume this boy. And we're going to resume this strand and it's going to start up here and going to go until it gets to the next thing and then it's going to pause. And it's going to event, it's going to come back, it's going to resume. And this is just a transformation of what we were doing with the callbacks. Except instead of scheduling a callback to do when the operation has completed, there's just one coroutine and we keep resuming the same one after each new operation has completed. And so we have the continuity of this thing because a coroutine is an object that remembers where it exited last and where it can resume to, and it also remembers all of its local variables that have been created up to that point. And it's a beautiful construct. And what's happening, the compiler is free to do whatever it wants, but the implementations that I've read about, what they do is they just takes your coroutine here that you wrote and it transforms it into a state machine that it is going to run for you. That's what the compiler's doing. It just makes a state machine out of this. So it's all state machines. It's just, you pick your poison. And this is by far the most elegant poison that you can have. And again, like I said before, I've said it many times, I just scratched the surface of what you can do with, awaitables in Asio here and what you can do with coroutines in general. It's a whole other bag of worms and there's crazy, amazing things you can do with them, but it would not fit into this video or its own video. It would require many videos to go over all that stuff. This is what I wanted to show you. Moving forward, I'm not sure what's next for the Asio playlist, if there's anything that I'm going to go over in the future or if I'm just going to leave it at this, or just, in multi-processing, asynchronous processing in general, if there's anything else I'm going to do. I don't know. We will see what the future holds. But until then, thanks for watching. Hope you enjoyed this video. If you did, please click the like button, helps a lot. And I will see you again, maybe, with some more Asio or C++ multi-threading.